Okay, so today I want you guys to be thinking through this proportion and rates stuff that we've been doing in class in the context of graphs. And so in particular, we're going to start by looking at distance time graphs. You might have met these back in year 8 last year, but we might have a closer look at them now. So first thing you might have seen was if we have a flat line like this, okay, what that means is that time is passing but distance isn't changing. Okay, so that means the person or car or whatever is staying completely still then. Okay, and so the word we use for staying still is stationary. Okay, so time's passing but the position isn't changing, and so it's completely still. Okay, that's a boring case. Better is if things are moving, which is when the line is not completely horizontal. Okay, so we're going to compare two different lines here, and what we want to think about is how do the speeds of these two moving objects compare with each other. Okay, so to measure speed, we are going to take a unit of time. And so first we're going to look at the yellow line. In this unit of time, the yellow, whatever thing it is, like a car or something, the yellow one only manages to travel this much distance. Okay, but in the same unit of time, the blue one manages to travel that much distance. Okay, so that's why we say the blue one is faster than the yellow one, because in that same unit of time, the blue one can cover a lot more distance than the yellow one could. Okay. And so what we see from this is on these distance time graphs, steeper means faster. Okay, and actually if you think back to the work we did on straight line graphs and gradients and those things, we can see that this is actually a very precise statement, and by that I mean that speed is exactly gradient. Okay, so speed means the same as gradient, which is rise over run. And I think this would agree with what you've learned in science or other things where the speed of an object, if it's traveling at constant speed, can be calculated by doing distance traveled over time taken. Okay, so you can see how the rise in this case is distance and the run is the time. Okay, so speed is exactly the gradient of the line, the slope of the line. Okay, all right, so pinch some questions from your book. Question 2a has a graph like this. It asks you to describe the journey and to actually talk about the speed of the car at different lengths of the journey. Okay, so what you see is two separate lengths of the journey, and so the first one is where it, for the first hour, only travels 60 kilometers. Okay, so it's 60 kilometers traveled in that first hour, and then in the second hour, it manages to travel 120 kilometers. Okay, and so again, the gradient is the same as speed, and you can see why here, because for the red part of the journey, it manages to travel 60 kilometers per hour, but in the green part of the journey, it travels at 120 kilometers per hour. Okay, so the way we can phrase our answer is something like this. The car travels at 60 k's an hour for 1 hour, and then at 120 k's an hour for another hour. Okay, so 2 hours, 180 kilometers in total, but that's how it's broken up. Okay, so you're comparing distance traveled with time taken, dividing them. It's a normal gradient calculation, but that gives you the speed. Now, in general, though, cars don't travel like this. Okay, they don't just move at constant speed all the time. They probably do if it's like a freeway or something, but generally you are starting and stopping, and your speed ends up a bit more like this. Okay, where it's actually changing all the time. That's why there's curves. Okay, because the slope is always changing, as we discussed a bit when we looked at nonlinear graphs a few weeks ago. So for example, at this particular point here, if you want to think about the speed there, what you really have to look at is like a little piece of the graph, okay? And you think of the slope of that little piece, right? And so if you sort of do this over the course of the whole graph, what you get is a whole bunch of speeds that are always changing. Okay, so you might see at point A it's quite steep, at point B it's almost completely flat. Okay, it's almost stationary, and so on. So the speed is always changing, as you can see with those arrows. Right? And a helpful way I normally think about it with is that I imagine a person sort of moving along this curve from left to right, and you sort of track how steep this climb is, okay, how steep the hill is. Is it going uphill or downhill, how steep it is. And so, for example, at this particular point, at point B, you can see this person is on a completely flat ground, and so that would be stationary. Okay, and by contrast, at point A, you can see this guy is on a very, very steep kind of hill, and so that's where it's moving very, very fast. Okay, so whatever way you want to think about it, with these curving graphs, they always represent changing speeds, and so you want to look at the slope at every point. Okay, so either by thinking about little arrows moving or about a person on a hill, whatever it is, okay, you're thinking about the slope at every particular point. We don't have a very precise way to analyze this stuff just yet, and to do that we need to use something called calculus. I think I've talked a little, really briefly about that at some point a few weeks ago, but calculus is really answering this question of how do we think about speeds at every point in time when it's changing all the time. Okay, so how do we actually measure the speed at every point, right? Which we can do when we have the tools for it, but that's later, maybe 2 years' time, or this year if I get bored. Okay, so I guess the main point of this though is that if your graph is curving like this, it means you're going from a shallow or a low speed to a very steep or very fast kind of speed, and so that would be an accelerating kind of graph. Whereas if it looks like this, you're going from steep to shallow, which means from fast to slow, and so that's decelerating or braking. Okay, so that's how we sort of think about these distance time graphs. I think the main difference this year is we are looking at some numbers, we can actually calculate some speeds, and then we can think a bit more closely at these changing speeds. Okay, I guess one application of this is not so much about distance and speeds and times and those things. Actually, a lot of graphs can be analyzed in this way. Anything that's changing can be analyzed in this way, where steeper means it's moving faster and all those things. I found this graph I thought might be interesting to look at. It's about the popularity, based on Google data, about different social media things, right? So you can look at it yourself. Like the white one or the grey one is MySpace, the white one's Instagram, all those different things like that. All right, and I'd actually like you to maybe I'll leave the work in the description. So look at the description below, and I'll give you what I want you guys to do. But part of it, after getting most of the core work done, I'd like you to actually have a bit of a look at this graph more closely and describe what's happening, describe the story, and even do some research as to what happened, what caused these things to, shoot up or dive as they did. You might see some interesting things there already. All right, so do the work from the book first. I think we've got to get that done, and then have a play with this. Okay, see the description for details, and I will see you next week. Have a good weekend. See you later.